right, today's lecture is a Good Friday lecture. We got two different topics / algorithmic problems, and each of them has sort of a really brilliant, cool idea that's not too hard to understand after you see it and doesn't require a lot of deep math. So you'll be able to spend the weekend thinking about how awesome randomized algorithms is without having to stress over the details of it. I am picking up from the Wednesday lecture on general sampling and polling, and we will be building upon it, using it in more sophisticated ways. So just to make sure we're all on the same page, I'm going to remind you of this magic number, mu sub epsilon delta, which is order, order of 1 over epsilon squared, and then the natural log of what, or I should just say log of 1 over delta. And this is sort of a magic number where you can say that if your expectation is mu epsilon delta, right, then the probability that you are outside of 1 plus or minus times the expectation is smaller than 1 over delta. Whoops. Smaller than delta. So basically, once you've got a large enough expectation, you can say that, and this is for binary events, right? You've got some expected number of successes in your experiment or something. And if the expected number, so I should just say this is some sort of 0, 1 random variable, or a sum of, right? So if you have a sum of 0, 1 random variables and you expect mu epsilon delta of them to be successes, then you'll probably be very close to the expectation. And as I discussed last time, there is a polynomial dependence on 1 over epsilon. So if you want really, really close accuracy, you'll generally need a very large expectation, which translates into needing a large number of samples. On the other hand, the dependence on delta, your likelihood of success is logarithmic, so you can drive for a very high confidence without dramatically increasing the number of samples, right? And let's see, did I use the word FPRAS in my Wednesday lecture, right? So we talked about fully polynomial randomized approximation schemes, which are about finding an answer within 1 plus or minus epsilon in time polynomial in the input problem size and 1 over epsilon. And so these are obviously connected to each other. You can use random sampling in natural ways to get a fully polynomial randomized approximation scheme for all sorts of quantities of interest. And so in Wednesday's lecture, we looked at the streaming model of computation, where you want to estimate, how many items in this stream satisfy a certain criterion, or what is the number of distinct items in this scheme, so on and so forth. And we use these sampling ideas in order to get fully polynomial randomized approximation schemes for them. All right, aside from the count-min sketch, the rest of that was really just pure sampling. You just picked a random subset and analyzed it. right? Today we're going to be trying to be more clever about our random samples. And so the first application of that I want to talk to you about is transitive closure. So I assume that you're all familiar with the notion of transitive closure, right? You're given a graph G, a directed graph. You can write G star to be equal all the pairs UV such that there exists a path from U to V. And so G star is another graph, right? The G star notation emerges naturally because if you think of we talked in shortest paths about squaring and so forth the adjacency matrix, right? So if you square the adjacency matrix, you get things that are reachable by a path of length 2. If you cube it, you get things that are reachable by a path of length 3. So just G star just says multiply it by itself infinitely many times so that you get all the possible distances. Of course, you only need to multiply it by itself log n times, repeated squaring, to get all the paths, but that's where this notation comes from. And so this is another graph. The problem is that even if your initial graph is sparse, the final graph is often very dense, right? There may be a lot of pairs. Even if you just have a tree, you may be able to have a quadratic number of pairs that can reach each other. And this is a problem this creates problems of storage and of computation. And there are, in fact, many situations in which you're interested in that transitive closure and related problems. Databases are one example. These sort of reachability problems arise in databases. They arise in social network analysis. Many other applications. But in some of these applications, you can often get at the same answer in multiple ways, right? If you've taken databases, you know that there's this notion of query optimization, that you have a query that involves lots of joins, and the order in which you perform the joins can really influence the performance of the query solver. And so you want to find a good set of joins to perform. And one of the things that determines whether a sequence of joins is good or bad is how many intermediate results you end up with, right? If you do the joins in one order, you may get a tremendous number of intermediate results. If you do the joins in a different order, you may get a very small number of intermediate results. That small number of intermediate results leads to a better performance, often. And it's similar with reachability. You may have several steps of computation or several ways of solving the computation, and the decision about whether to take a particular transitive closure may depend on the size of that transitive closure, okay? And so that's just a long-winded way of saying that there are real reasons in practice for figuring out the size of a transitive closure without computing it, because you may have the option of computing this transitive closure or computing a different transitive closure or not computing the transitive closure at all, and you want to know what's going to be the outcome without actually doing the work. Okay? Now, unfortunately, nobody knows how to compute the exact size of the transitive closure without actually computing the transitive closure. But for these applications, a fully polynomial randomized approximation scheme is certainly sufficient. It's really enough to get within 1 plus or minus epsilon. That's what's determining the performance of your algorithm, not the exact constant.
So we're just trying to compute this graph, the G star?
So the point is we don't want to compute the graph. We want to try to, because that could end up taking, right, if we have an n vertex, n edge graph, we may end up with a size n squared output, right?
Can we not characterize it using equivalent linear time for determining the algorithm?
No, not the.
All the strongly connected components in the direction of the DAG.
But the question is, what is the reachability structure of the DAG? It could be very sparse or it could be very dense. Okay. Yes?
We just computed the size.
That is correct. So that's what I'm saying. That at the end of the day, a lot of these applications are going to want to compute the transitive closure, but as a useful step about deciding on their process, whether they do it now or later, whether they do it with this graph or that graph, computing the size is useful. Yeah? Yes. Well, let me see. I can, but I don't know if I want to take. I don't know if I want to go through it. If you know the size of the graph that you are going to end up with, then you can estimate how long a certain computation is going to take. And therefore, you can decide whether it is worth doing the computation this way or perhaps using some other method that does not even construct the transitive closure. Okay? Yeah? Exactly. Size is number of edges. We know the number of vertices. The number of vertices does not change in the transitive closure. Okay? All right. So that was motivation. Let's dive into how do we actually estimate the size of the transitive closure. Okay? And let's start by asking how I can estimate the size of the transit or what's reachable from one vertex. Okay. And for starters, let's suppose I had a magic function that tells me, here's a pair, u and v. It'll tell me whether you can reach v or not. Okay, so I have some sort of local tester for that. Is there a path from u to v? If I have such a tester, how might I estimate how many vertices can be reached from u? Yeah? Exactly. Or candidate neighbors, or candidate reachable vertices, right? So what I can do is choose random vertices. Let's call this vertex I want to start from u. Check if they are reachable from u, right? This is a standard sort of statistical test, right? I choose a thing and I see if it is in the set or not. And this gives me an unbiased estimator for the number of vertices in the set, right? What do I need to do in order to make sure that that estimator is accurate enough? Yeah? Exactly, right? Repeat k times, right, until you get about mu sub epsilon delta reachable. And now you can declare that you have an accurate estimate. And I think I talked about this in the recording, right? You need to be, this is not literally true, like there's some 1 plus or minus epsilons to worry about, but it's in this ballpark, right? If you, the natural thing to do, right, if you have to repeat it k times until you see mu sub epsilon delta, in order to see mu epsilon delta successes, you would, the natural thing to assume is that the reachability probability is mu sub epsilon delta over k, right? Would be the natural thing that you conclude, right? This, it turns out, is not an unbiased estimator. This actually has a slight upward drift from what you want, and the correct unbiased estimator is this quantity for, I mean, you can go look at the math if you want to, okay? Mu epsilon delta over k is what's called the maximum likelihood estimator, which is not quite the same as an unbiased estimator. But the point is these are all close to each other, and they will all satisfy the within epsilon with probability 1 minus delta, okay? And I'm not going to do the math in detail because I did it last time. I mean, that you can see that in the recording. For now, we'll just assume that you understand that there's some 1 plus or minus epsilons here that you need to correct for. Okay, so how many times am I going to have to, like, it says repeat until you see mu epsilon delta reachable vertices. How many samples am I going to have to take in order for that to happen? Well, from last time, if the reachability probability, right, if the probability of random vertexes reachable is p, then I'm going to need about mu sub epsilon delta over p samples in order to see the mu epsilon delta that I'm looking for, right? Again, plus or minus epsilon, all right? And what is p if I'm talking about a graph with n vertices? Yeah? Exactly. So the number of reachable vertices divided by n. So this quantity is going to turn into mu sub epsilon delta times n over, I'll call it r, the number of reachable vertices. Okay. So that can, now I can kind of read off a runtime, right? If I have a magic oracle that tells me whether something is reachable or not, I'm going to need to invoke the oracle about this many times. Now, of course, the problem is that the reachability, there might only be one vertex, namely myself, reachable from me, which will make this mu epsilon delta times n, right? And if I want, remember, if I want a high probability result, then delta needs to be log n or so, or 1 over a polynomial, which means that I'm going to need n log n samples in order to be confident that this vertex can only reach itself. Okay? And this was assuming a magic oracle that tells me whether I can get from u to v, right? How much time does it actually take to decide whether I can reach a vertex from another vertex? Well, you have to do a depth first search, or you have to do a search, right? So it might actually take you linear time just to decide whether you can reach v from u, right? So if you have to take n samples and each of them takes you m time to do the reachability check, you're already at mn time, which is actually the time that it takes to compute the transitive closure explicitly, right, by doing a search from every vertex. So that's not very helpful. But let's start thinking about whether we can conserve some work, do a little less of this, right? So here I was talking about what's reachable from u, and the idea was I'll choose a random sample of vertices and I'll check whether u can reach them. But if I'm going to be doing the transitive closure, I need to do this from every u, right? Right? But do I need to start over again from every u? Do I need to pick a new set of samples for each vertex u? Yeah?
Really, just do a search on the opposite graph from the sample.
Exactly. If I pick a single vertex v at random, right, I can decide all of the u's that can reach v, and therefore get information about the reachability set of every vertex by that one sample v, right? And the information comes from just searching backwards from v to see all of the vertices that can reach v, right? So choose a random v and search, or actually I'm going to say send a message for reasons that will become clear. Backwards to every u that can reach v. And this is only going to take me order m time, right? So this is conserving work. I don't have to do it separately for each vertex u. Instead, with just one linear pass, I get a sample for every single vertex, right? And I learn about the reachability sets for every vertex. So this is a little bit more promising because this means that the time is sort of order, right? The propagation work times this magic number times the worst case 1 over p, right? If every vertex can reach a lot of vertices, then every vertex is going to get messages relatively quickly, and I will learn about every vertex relatively quickly. Yes? But this still doesn't help you deal with those leaves, right? That can only reach themselves, and you're going to need to take, right? P in the worst case can be 1 over n, in which case you still end up with an mn time bound. Okay? So now comes the clever, fun bit, right? And this is due to Edith Cohen, researcher who was at AT&T, I think, at the time, now at Google, who's done some very nice work on problems, very nice research in randomized algorithms. If I take this message perspective, right? So I pick a random vertex and ask it to message all of the nodes that can reach it so that those nodes can build up their knowledge about the graph. Okay? So we're repeating this process. Here's a node that starts receiving messages. And at some point, this node has received that magic number, mu epsilon delta messages, and this node knows how many vertices it can reach to sufficient accuracy, right? So that's very nice. This node can stop paying attention to other messages, right? It knows enough already, okay? But there's actually something stronger that I can say than that, okay? So after a given node x receives mu epsilon delta messages, it doesn't need any more, right? But what else doesn't need any more messages? Right? This node, we know, X has received all these messages, it knows enough. I claim that we know a lot more. Yes? Exactly, right? Anything that can reach X has also received mu epsilon delta messages. Right? Which means that it doesn't need any more. And that means what? So X gets this message. It doesn't need it. Does it? But nobody it can reach needs it either. Nobody that can reach it needs it either. So if it gets a message and it's already received enough of them, it can just drop that message on the floor. Right? So let's think about what the runtime of this algorithm is going to be if vertices get to drop messages after they've received mu epsilon delta of them. Right? So we're doing exactly the same process. Pick a random vertex, send messages. Pick a random vertex, send messages. The only difference is that when that message arrives at a node that has received enough, it drops it. Okay? So what can we say about how much time this algorithm is going to spend propagating messages? So focusing on the vertices doesn't quite give us what we want, because we can say, okay, this vertex has received mu epsilon delta messages, but that doesn't say anything about, like, it may receive a lot more, which it proceeds to drop. But is there another way that we can do the accounting, instead of focusing on vertices, that will allow us to say that not a lot of messages get sent, as opposed to saying not a lot of messages get received? Yeah?
So across every edge of epsilon delta equals double.
Exactly, right? So if I look at a particular edge, the head of that edge, after it receives mu epsilon delta messages, will not pass on anymore, right? So vertex at head of an edge will only pass on mu epsilon delta messages. To that edge, which means that each edge carries only mu epsilon delta messages. Which means that we only spend order m mu sub epsilon delta work delivering messages. And that's kind of most of the work of the algorithm, right? Besides the message delivery, what other work is the algorithm doing? Yeah? Generating samples, right? So we pick a vertex. So the algorithm is pick a vertex and then send messages. Pick another vertex, there's accounting work that happens when a message arrives, but that can be part of the message sending, right? So there's picking vertices and sending messages. We have just bounded the work of sending messages by mu epsilon delta. What about the vertex picking work? Maybe we have to pick vertices forever. Well, let me ask the same question. After I've picked a particular vertex, mu epsilon delta times, what can I say going forward? Right? Who's going to be interested in the messages from that vertex if I've already picked that vertex mu epsilon delta times? Well, the answer is nobody, right? For the same reason as we said before, right? If I got picked already mu epsilon delta times, it means everybody who can reach me has already received mu epsilon delta messages, right? So there's no need for me to transmit after I get picked mu epsilon delta times, right? So that tells me that there is only mu work per vertex. Right? And I mean, you have to do a little bit of sort of thinking about it or accounting, like you still may need to pick the vertex. You still may pick the vortex more than mu epsilon delta times, but once you've picked every vertex mu epsilon delta times, you're done, right? So we are done once every vertex is picked mu times. Now, how long is it going to take for every vertex to get picked mu times if I am randomly picking vertices? Let's try a particular vertex. How long is it going to take for vertex 1 to be picked mu times if I am picking vertices at random? Yeah? Good. So let's break that apart. So if I'm looking at a specific vertex, right, and I do n mu picks, then the expected number of times that I pick that vertex is mu, right? So that vertex has the proper expectation. And of course, because mu is mu epsilon delta, I can say that I will have picked that vertex at least 1 minus epsilon mu times with probability 1 minus delta. That's the definition of mu, right? Okay, so again, fudging with the constants a little bit, if I multiply those picks by 1 plus epsilon, then I will have picked it mu times with probability 1 minus delta. So that gives me a high enough probability of picking that vertex, right? Probability 1 minus delta. But I want to pick all of the vertices. I want to get mu picks from all of the vertices. So what do I have to do in order to have confidence that I have picked all of the vertices mu times? So since these answers are not coming fast, I'll do this a little bit more carefully, right? So the claim is that if I look at vertex X, that after mu divided by 1 minus epsilon times n picks, right, I will see X at least mu times with probability 1 minus delta, right? And that just follows from the fact that I have a 1 over n chance of picking vertex X each time, so the expected number of picks is now mu over 1 minus epsilon, and so now I plug in my my Chernoff bound, right, or my usual bounds, all right? How do we ensure that all of the vertices have been seen mu times? Yeah? And how do I show that I can stop relatively soon?
Well, you just said that, like, after a reasonably short amount of time, every vertex will have been picked few times.
Yes, but my probability here is 1 minus delta. So if delta is 1%, but I have millions of vertices, I can't have this. That's not enough to guarantee that I've seen all of the vertices many times. Yes? Exactly. What I do is I change from delta to delta over n, and then I take a union bound. Right? So if my ultimate target is mu epsilon delta, I instead work with mu epsilon delta over n. so that the probability of failure on a particular vertex is only delta over n. Then I can take a union bound and say that the probability of failure over any vertex is only delta. Yes? Ask questions if that's not clear, right? So now the probability of failure on a specific vertex is delta over n. So probability of failure on any vertex is less than or equal to delta by the union bound. Okay? So I need, in summary, I need n times mu sub epsilon comma delta over n samples to have mu epsilon delta, or sorry, divided by 1 minus epsilon, to have mu sub epsilon delta of every vertex. Yes? And at that point, I've learned everything, like every vertex has learned everything it needs to know. So in summary, right, we are picking this many samples. Sampling is constant time. We are doing that much message passing. We now have an algorithm whose overall running time is just this. Linear times the magic mu number. Yes? And plugging in our typical values, right? So if we want to state a high probability result, it means we want delta to be 1 over a polynomial, right? Which will make mu epsilon delta over n log n over epsilon squared. So our high probability runtime for an epsilon approximation is just this, almost linear. So a factor of n speed up over the naive method for computing the transitive closure. Any questions? Great. So you can, yes, go ahead. It's an interesting idea. I suppose it's conceivable that you could. It's conceivable that you could shave. Well, I don't know if you can shave off the log n factor, but maybe you can shave it off of the m. I think you probably still need to pick log n times from each vertex, but even that might not be true. Yeah, the one thing I worry about is that given how close this already is to linear, you might only be getting improvements in your constant factors by doing that sort of cleverness. Okay. All right. That was algorithm 1 for the day. And it's a little bit early, but I think it's the obvious place to take a break. So let's do that, and then we will look at problem 2 for the day. Nobody wants a break, huh? I can put on some music if it'll help. You know, in my advanced algorithms class last year, people were doing push-ups in stadiums during the break. Yeah, you're very passive. All right, given the enthusiasm with which people are approaching the break, let's get back to class. We're going to look at a very interesting canonical problem called DNF counting. So what does this mean? What is DNF? Well, we're looking at the satisfiability problem, right, which is this famous NP-complete problem, right? And SAT, general SAT, is about you have an arbitrary logical formula, right? Ands and ors and nots and so forth. And the question is just, is there a way to assign truth values to the variables so that the entire logical formula is satisfied, right? And this is the canonical NP-complete problem, the one that's used to sort of develop a whole theory of NP-completeness. You show everything can be reduced to this one, right? And one of the first things that's shown is that if you move to conjunctive normal form, you don't change anything. So the conjunctive normal form is one where you have a bunch of ors anding a bunch of other ors. And so on, right? And so this is a very strong restriction on the shape of your logical formula, but it turns out it doesn't help you. This is still NP-complete, okay? And in fact, even 3CNF, where you only have 3 literals in each of the, right? So each of these is called a clause, the thing that's in the parentheses, and within the clause you have things called literals. Okay. So 3CNF is a form where all of the clauses have at most or exactly 3 literals in them, and that's still NP-complete and something that we can't expect to solve. Okay. Now, by symmetry, you might think that the same is true of DNF, right? So this is disjunctive normal form. And this is where you put the ands on the inside. Right? And I mean, you can get one of these simply by negating a CNF, right? If you, right, Dermov's theorem says that if you take the negation of a CNF, you get a DNF. So is this just as hard to solve? I see shaking heads. Why is it not hard to solve this problem? Yeah? But it's not an exact algorithm. Yes?
If you have like a DNF formula, you could just check, try each of the clauses, and it's really easy to check whether if you just have a bunch of ands.
Exactly. Right. So the DNF formula says, right, you satisfy the DNF if you just satisfy any one of the clauses, because there's a bunch of ors out here. So all you need to do is figure out how to satisfy one of the clauses. How do you figure out whether one of the clauses is satisfiable or not? Yeah? Exactly. The only way to prevent a clause from being satisfiable is if it has both x1 and not x1, right? Or something like that. As long as as long as each variable only appears with one sign, what do? Well, you set it so that it's true with that sign, right? If it's not negated, you make it true. If it is negated, you make it false, and that makes your clause true. And that makes the DNF true, right? So satisfying a DNF is trivial. Satisfying a CNF is NP hard. Strange, right? So where did the hardness go in the DNF? Yeah? Well, that's true, but not if you start with the CNF, right? If I start with the CNF, it gets the same number of clauses after I do the swap. Right, so where did the hardness go? What's hard about a DNF? Yeah? Exactly. With DNF, what's hard is finding a non-satisfying assignment. Right? Something that makes the thing false. Okay, so it is symmetric, but you have to flip your notion of true and false at the same time as you're flipping from CNF to DNF. Okay, so we have an NP-hard problem, we have a trivial problem, right, the solvable linear time. But given that we understand so much about it, we need to, as theoreticians, we need to make the problem harder, right, so that we have something interesting to study. And what theoreticians asked was, how many satisfying assignments does this DNF have? Or does this logical formula have? Okay. So stat counting says, here's an arbitrary formula. Tell me how many different ways there are to satisfy it with different assignments of the variables. Okay. Now, if you could answer that question exactly, you could answer the SAT and CNF questions, right? If I can tell you how many satisfying assignments there are, then I can tell you whether there is one, right? And that answers these decision problems. So that tells us that counting the number of satisfying assignments to an arbitrary or CNF formula is NP complete. Okay? But that doesn't tell us anything about DNF counting, right? That argument, right? I know how to tell whether a DNF formula is satisfiable or not, so maybe it's also easy to count the number of satisfying assignments to a DNF. Can anybody give me a reason that it's not? Yeah? Exactly, right? If I ask how many satisfying assignments there are for the DNF, and the answer comes out to be 2 to the n, that tells me there are no unsatisfying assignments, which tells me that if I look at the complementary formula, that there are no satisfying assignments for the CNF, right? So if I could count DNFs, it would let me count CNFs, right, by inverting. And so counting DNF assignments is also NP hard by this trivial argument. But in fact, it's worse than that. So counting the number of satisfying assignments is sharp P hard. Sharp P is the complexity class of asking how many assignments, how many different solutions are there to an NP hard problem? Or sorry, to a polynomial time solvable problem, right? So sharp P is asking about the number of solutions to a problem in P. Okay? And we've already seen that sharp P contains NP by the argument we just made, right? If you could answer how many solutions there are, you could be solving NP hard problems, right? So this is at least as hard as NP. And we think that it's worse. I should add that actually, if you work through the complexity theory, DNF counting is Sharpe complete. So there's the analogous notion of completeness. We've talked about NP completeness and P completeness. So DNF counting is of the hardest problems in Sharpe P. And you can reduce all sorts of other problems to DNF counting, or you can reduce DNF counting to all sorts of other problems, right? Which shows that DNF counting is the hardest. So we're not likely to get an exact solution. What's cool is that it turns out that you can get as close an approximation as you want. We are now going to develop a FPRES for DNF counting. And let's think about why this is hard. Okay? So, given all of our discussion about random sampling and polling and so on and so forth, what would be the most obvious algorithm for estimating the number of satisfying assignments for a DNF? Yes? Yeah. So our idea might be choose random assignments and check what fraction satisfy. Okay. So this already draws the equivalence that like counting the number of satisfying assignments is equivalent to just determining the probability that an assignment satisfies, right? Because we know the total number of assignments is 2 to the n, if we have n variables, right? There are 2 to the n assignments to n vars, so the number is just equal to 2 to the n times the probability. But this also points at the problem, right? The probability is the number of satisfying assignments divided by 2 to the n. Why is that bad? Yeah?
Like if we have a situation where like the number of satisfying assignments is, let's say, like 2 to the n over 2, and then like that.
Wait, let's be more aggressive. Can you give me an example where the number of satisfying assignments is 1?
We could have something where like you just like have a single clause with just like that's the end of everything.
Exactly. So if I have one clause, right, this has exactly one satisfying assignment. So that means that the probability that I get a satisfying assignment is 1 over 2 to the n. So how many samples am I going to have to take in order to estimate the probability?
Almost 2 to the n.
Worse, right? You need 2 to the n times mu epsilon delta samples to estimate. Okay, and this is the most common challenge in sampling-based algorithms, is just rare events. Right? If you're trying to estimate something, estimate the probability of an event, count things, right? If it's really small, if the items are really rare, you're going to need a huge number of samples in order to get the estimate that you want, right? And I mean, this came up even with the transitive closure, right? The problem was these vertices that could only reach that could only reach themselves, right? So your sample very rarely would pick something that they could reach, so it took you a long time to get an estimate for the reachability from those vertices. So rare events are bad. Yes, a question? So is this a problem? That's a very reasonable question, right? If you have a 3 DNF, right? Now, right? If you have a 3 DNF, then the first clause is going to be satisfied with probability 1/8 when you take a random sample, right? So that's actually a very good point, right? This is not a problem if even one clause is short, right? So if you have a 3 DNF, right, then your P is at least 1/8. And so you'll only need mu epsilon delta samples and everything is lovely, right? But if all of your clauses are long, right? And as soon as they're longer than log n, as soon as they have more than log n variables, your probability of satisfaction drops below a polynomial, and so the number of samples you need rises above a polynomial. So that's no good, okay? So what do we do about that? How do we fix? I mean, there are various approaches to fixing rare events. One that often works well, and that works well here, is to change the sample space. Okay. So we can talk about having, AI is this set. This is just so I can draw a picture. AI is the set of assignments satisfying clause I. Okay? So I can draw this giant sample space, and somewhere in here is A1. Okay? Also somewhere in here is A2. Also somewhere in here is A3, right? And so on. And the problem is that if we throw darts at this giant sample space, we will never hit the stuff that we're interested in, right? So what we're going to do is change the sample space. We're going to change the sample space into one where we are likely to hit the stuff that we want. And in fact, we're going to make the sample space exactly the assignments that we care about, that satisfy a clause. Okay? Let me draw this in a slightly different way that'll make it easier for us to generate that sample space. I'm going to consider what's called the disjoint union of the AIs. Okay? So what I'm going to do is I'm going to make a giant table, notionally. I'm not going to actually write this down for the algorithm, right? Where I have these different, let's see, no, I don't want to do it that way. At the top, I'm going to have clauses. Clause 1, clause 2, clause 3, clause 4. Over here, I'm going to write assignments. Okay. Now I can go through this table and mark off which assignments satisfy which clauses, right? Now, there might be some assignments that don't satisfy any clauses at all. I'm not interested in those, right? What I want to do is count the rows with at least one x. Does that make sense? How can I count the rows with at least one x? Well, notice that it's easy for me to tell how many x's there are in each column, right? I know how many assignments satisfy each clause separately. Yes? So I know how many x's are in this column. I know how many x's are in this column. I know how many x's are in each column. What does that allow me to do? Well, it'll let me pick a random x, right? If this column has 20 x's and this has 10 and this has 5, then with probability 20 out of 35 I pick from this column, and with probability 10 out of 35 I pick from this column, probably 5 out of 35 I pick from this column. And I can also generate easily, I can pick a random x from a particular column, right? What does it mean to pick a random x from a specific column? If I remember that these are all assignments. Okay. I know the size of each AI. So I know the sum of the sizes of each AI. So I can choose column I with probability AI divided by the sum of the AJs. And then I can pick a random x from column I. What is a random x from column I, and how do I pick one? So column I is about clause I, and I put an x on an assignment that satisfies clause I. So what does that mean? Yeah? Exactly. I set the vars that are, or the literals, that are determined by clause I, and I set the others randomly. Right? That gives me a random x from the table. Now, what I'm actually interested in counting is the number of rows that have an x. Right? Does a random x from the table correspond to the number of rows? Well, no, because there might be many x's in a particular row. Right? But how can I sort of relate these two quantities? Well, what I can do is I can pick a canonical x from each row and put a circle around it. Okay. Doesn't really matter what my rule is for calling an x canonical. I am going to use the rule that it is the first x in the row. Okay? In other words, the special x's are the ones that satisfy the first assignment in their row. Okay. What can I say about the number of circled x's? Yeah? Exactly, right? Number of circles equals number of satisfying assignments, which is just the number of rows with an x. Yes? So if I could just figure out what fraction of the x's are circled, this would tell me what I need to know, right? Because I know how many x's there are. I just need to estimate the number of circled x's. How long does it take me to do that? Right? So I know the number of x's. I want the number of circled x's. What does random sampling tell me about the way to estimate that number? Yeah?
Like for each column, you could try to like at least sample from that column, which we know that we could do, and like, and also like after we get a sample, we can just like check it satisfies other process before it to see if it's like
Exactly.
or not.
Exactly. What you're pointing at is that we're just going to use regular random sampling here, right? Choose a random x, and then check if it is a circled x. Right? That is an unbiased estimator for the fraction of circled x's. Right? Forget about where this all came from. If you just look, this is clear if you talk about the table, right? We have this table. If I pick a random x and check if it's circled, since there's only one circle per row, estimating the number of circled x's, picking a random x and checking if it's circled will give me an estimate for the number of circled x's, which is an estimate for the number of rows. Yes? Let's flesh this out. How do we choose a random x? Well, I said that already, right? We pick a column with appropriate probability based on the number of x's in each column. In other words, based on the number of assignments that satisfy each clause, right? And then within the column, we pick a random satisfying assignment for that column using the observation that we set the variables for that clause and set the other variables randomly. And that gives us a random x in the column. How do we check if it is circled? Right, so we pick our random column I, and then we pick an x from it. What does it mean that it is a circled x? Yes? Right, so we check that no clause before I is satisfied. Right? We circled the first clause in each row, so if no clause before the column that we picked is satisfied, it means that the column that we picked has the circled x. Yes? All right, so this is clearly polynomial, this is clearly polynomial, right? And it gives us this unbiased estimator. Now the question is, so that's what we need, right? We do this a bunch of times, and we see what fraction are circled, and that gives us our estimate for the fraction of circled x's, right? How many trials are needed? What determines the number of trials that we need to do? All right, let's answer that more basic question. What determines the number of trials that you need to perform in a sampling experiment like this? Yeah? The size of the sample space actually doesn't affect how many samples you need. That's what's great about random sampling. right? With random sampling, even though there are, whatever, 350 million people in the United States, I only need to pick 30 at random in order to get an estimate for their, red-blue color or something like that, right? So what does determine how many samples I need? Yeah? Exactly, right? The number of samples that we need is always mu epsilon delta divided by the probability of success, which in this case is that we get a circled x, right? So all we need to figure out is the probability that we get a circled x. Okay? Now, we can't figure out exactly because it depends on the problem, but can we bound it? Right? And notice, we need a lower bound on the probability of success if we want an upper bound on the number of samples. Right? So is it possible for the probability of success to approach 0? Let's look at one specific row. If you're just sampling from a specific row, what's the smallest possible probability of success? Yeah? 1 by number of columns, right? In a specific row, there's at most 1 x per column, and one of them is circled. So the probability that you get the circle in that row is 1 by m, where m is the number of clauses, right? But this is true for every row. So it's true for the whole table, right? Another way to put it is that the number of circles is, or sorry, let me put it the other way around. The number of rows, no, let me put it even a different way. The number of x's is at most the number of clauses, which we'll call m, times the number of circles, right? Because each circle appears in some row, and at worst you have m other x's in that row with the circle, right? So we push this around, and we find out that the number of x's divided by the number of circles, sorry, other way around, number of circles divided by the number of x's is bigger than 1 over m. And this is my probability of success when I pick a random x. So back up here, the number of samples that we need is proportional to the number of clauses. Right? So this is great, right? We had this exponentially sized sample space. Or to put it another way, is a sample space where what we care about could be exponentially small. What we did is we changed the sample space into one where the things that we care about were no longer rare. Right? We had to use this clever trick of actually duplicating some of the sample points. But that gave us a sample space where the set that we care about is large. Okay? Now, this is not the runtime because we still have to look at the time that it takes to check whether a clause is satisfied or not. Or, sorry, whether a clause is circled or not, which means evaluating that clause at all of the other, evaluating the assignment on all of the other clauses. So this takes time proportional to the size of the formula. You're essentially going to be evaluating all of the other clauses, right? And by size of formula, I mean the whole written out. I don't mean the number of clauses or the number of literals, because you're actually going to end up evaluating the entire formula to check which other clauses are satisfied, right? But this is still a very fine runtime, right? Number of clauses times size of formula times our favorite tiny number. Okay? Any questions about this? Okay. I do it slightly more mathy in the notes if you want some formulas that work this out. But I think this gets the idea across. I will mention that you can do better, and in your homework you will do better. You can actually get rid of this term, okay? Because the way to think about it is we're trying to estimate a number, right? And we're doing that by computing we're sort of looking at a circle and asking how many asking if it's the first one, right? But what we're really asking is how many x's are in this row, right? If instead of taking just putting a circle around the first x, we could just divide up our attention over the many x's in the row. And so if you know the number of circles, the number of x's in the row, that provides you a different kind of unbiased estimator. But since we're only worried about approximating it, about an approximate answer, we don't have to exactly know how many x's are in the row. It's enough to estimate the number of x's in the row. And how do you suppose you estimate the number of x's in the row? I've only showed you one way of estimating things, right? Yeah? Yeah, you sample random clauses and check if they're satisfied or not, right? So that actually does away with this extra term and gives you essentially a linear time algorithm for this problem. It also generalizes further. I didn't even say it, but we took for granted that we were essentially setting, in our random sampling, we were essentially setting our each variable to true or false with probability 50-50, right? But you can generalize this to ask about, actually, I didn't say this. What we've done here is get an estimate for the number of satisfying assignments. But if you look carefully, we actually also gave an algorithm for generating a satisfying assignment uniformly at random from the set of satisfying assignments, right? So let me take just 1 minute to say that. Suppose that instead of counting, I wanted to generate a uniform satisfying assignment. I've already done all of the work. I just have to change my output. Right? What does it mean in our table to generate a uniform satisfying assignment? It means to pick a random circle. So how would you go about picking a random circle? Using all the machinery we just developed. It's hard to directly pick a random circle, but it's easy to pick an x, right? So how do you pick a random circle? Exactly. Pick x's until you get a circled one. Okay. And it's easy to argue that since you're sampling uniformly among the x's, when you get a sampled one, you're sampling uniformly among the circled x's. So this is not only an algorithm for counting satisfying assignments, it is also an algorithm for generating satisfying assignments uniformly at random. And the way we set it up, it generates them under the assumption that each literal is being set true or false with probability half. But you can generalize it to an algorithm that generates, that takes any probability of true for each of the variables, right? You can say, if assuming each variable is true with probability 1/3, generate me a random formula. And also, you can generalize the above to say, if I set every variable true with probability 1/3, what is the probability that this clause is satisfied? So this work all shows a very intimate connection between generating a sample and counting or deciding the probability of a success. And we will revisit that several times through the semester in different settings. So that's the end of this story, which I hope was interesting. Next week is going to be devoted to, this week was kind of about counting things, right? Like just estimating probabilities by polling. Next week is going to be graph algorithms. We're going to actually use these ideas of sampling to build solutions to graph problems like minimum spanning tree. Okay, so I'll see you next week.